Hello and welcome everyone. We are Team 11, the Northern Lights, and this is our final PDR video recording. These are the 11 awesome members of Team 11 from the science team, business team, and engineering team that make this mission possible.
Thanks, Kennedy. Yep, our mission intends to explore Enceladus, Saturn's icy moon. Its south pole is of particular interest for the hydrothermal plumes. This is where our mission will directly intend to land a robotic secondary payload and explore this habitability further. These are the main constraints, including the mass, the volume, and the budget.
With primary science objectives driven towards search for life and targeted biosignatures on Enceladus, the following instruments were chosen. All these instruments come with baseline and threshold specifications to meet and exceed mission requirements. Microscope for life detection, for which the primary module is atomic force microscope, detects small structures. Organic composition analyzer, OCA, serves as an organic indicator. Chemical composition of inorganics is explored in detail by the Raman laser spectrometer. Finally, GSS employs seismometer and geophone capabilities to analyze ice shell thickness and water table depth.
Our landing site proposal is located in Baghdad sulcus, the fissure that most researchers theorize was the first to form on the icy moon. Inside this sulcus, there are multiple plumes that constantly eject water vapor, ice particles, and most importantly, organics, directly from the turbulent ocean located beneath the ice shell of the satellite. Among these plumes, we focus our attention in Jet 37 because of one crucial reason. Historically, this plume has proven to be constantly active through the entire Cassini mission. Because of that, it is the spot with the greatest potential for life. Nevertheless, our team faced the challenge to work with the 0.33 meter opening of the fissure.
There are 4 kinds of instruments that will attain data which ensures the success criteria for the mission. OCA shall analyze any patterns or relationships between organic molecules with a variety of molecular weights and also characterize inorganic geochemical context. GSS shall measure the thickness of ice crust to 10 kilometers and establish core radius and density with 200 kilometers and 450 kilometers per meters cubed. AFM captures topographic images by distinguishing chemical heterogeneity on the surface and shows some contrast between inside and outside of the scanned region. VS searches for signs of life, employing the stepper motor to scan through a range of 10 millimeter surface and detect ancient carbon at low concentration levels.
This is the CAD that we created for the lander structure. Components are colorized to make them easier to distinguish. These are the separate components not shown to scale. The structural skeleton resembles a truss to give it a good combination of being strong and lightweight.
The entry descent and landing begins with the lander as a secondary payload above the aboard an Enceladus orbiter mission. The lander will separate itself above the North Pole of Enceladus and immediately perform an orbit lowering burn to lower its periapsis at the South Pole to 5 kilometers. At the periapsis, it will then perform a secondary entry burn, which will lower itself into a projectile descent trajectory, and finally a landing burn, engine purge, and airbag deployment at the landing site in the Baghdad sulcus fissure. Thus, after the lander is safely on the surface, it will begin its 60-hour operational period with communication relayed through the orbiter.
There are many components and parts on the lander that need to be protected, which is why we decided to use the integrated multi-level installation, which allows high performance at low conductivity using discrete spacers, which is very cheap, and it's able to be easily, quickly repaired if there are any trouble to occur. We also decided to use many layers to be able to act as both a thermal vault and a debris shield for small particle impact.
Our navigation system will be comprised of the LiDAR system, star trackers, guidance cameras and computers, a main engine, and 12 reaction control thrusters. The guidance camera and LiDAR sensors will work to direct terminal navigation controls, as well as a closed loop feedback system that will be used with the guidance computer. The LiDAR will provide altitude and fissure geometry information for the probe landing procedure as well. Our communication system is comprised of 3 microstrip transponders, 1 main high gain transmitter and receiver, as well as a secondary and tertiary medium gain receiver and low gain transmitter. All of our antennae should be equipped with ultra high frequency range.
The VES-16 lithium-ion cells are responsible for the overall mission. We chose the VES-16 batteries because it's notable due to its high power density of 390 watt-hours per kilograms. It requires a total of 1,600 watt-hour of power to guarantee the operation of a spacecraft over its 60-hour mission lifespan. The VES-16 power shall be charged from the orbiter during the approach and landing phase, which will contribute to the power to be available to the probe until it has been removed.
To make our mission possible, we have a budget of $400 million, which with it, we have 22 total staff, 7 scientists, 9 engineers, and 6 administrators. Our total expense is estimated to cost us $265 million, which falls under the budget. Our salaries is estimated to come out to $13.5 million, with equipment at $232 million, administrative and outreach about $20 million, and with a gross margin around $81 million. And as any mission, there is also an outreach component. Team 11 plans to reach 45 schools in low-income communities in New York City, where 15 will be elementary school, 15 comprises of middle schools, and 15 high schools. Outreach will consist of educational TED Talks about Saturn's moons and Enceladus. And also there will be an after-school robotics program for elementary school students. And for middle and high school students, they will receive JMARS and CAD workshops, which is a technical skill much needed in the field. Outreach will estimate to 5% to 8% of the budget, costing up around $20 to $32 million.
Our mission should begin 36 months after phase A starts, and that will start with the launching of our orbiter and payload. And this only requirement during the whole period for timing is that the landing occur around 15.8 hours after periapsis. This is to ensure that the plume fissure is maximum for entry. And on behalf of Team 11,
thank you. Thank you.
Thank you.
All right, that'll work out better.